Polar form of complex numbers. From previous classes, you may have encountered imaginary numbers, the square roots of negative numbers, and, more generally, complex numbers which are the sum of a real number and an imaginary number. While these are useful for expressing the solutions to quadratic equations, they have much richer applications in electrical engineering, signal analysis, and other fields. Most of these more advanced applications rely on properties that arise from looking at complex numbers from the perspective of polar coordinates. We will begin with a review of the definition of complex numbers. Imaginary number I. The most basic complex number is I, defined to be I equals the square root of -1, commonly called an imaginary number. Any real multiple of I is also an imaginary number. Example 1. Simplify the square root of -9. We can separate the square root of -9 as square root of 9 multiplied by the square root of -1. We can take the square root of 9 and write the square root of -1 as I. Square root of -9 equals square root of 9 multiplied by the square root of -1 equals 3I. A complex number is the sum of a real number and an imaginary number. Complex number. A complex number is a number z equals a plus bi, where a and b are real numbers. A is the real part of the complex number, b is the imaginary part of the complex number, I equals the square root of -1. Plotting a complex number, we can plot real numbers on a number line. For example, if we wanted to show the number 3, we plot a point. To plot a complex number like 3 minus 4i, we need more than just a number line since there are two components to the number. To plot this number, we need two number lines crossed to form a complex plane. Complex plane. In the complex plane, the horizontal axis is the real axis and the vertical axis is the imaginary axis. Example 2. Plot the number 3 minus 4i on the complex plane. The real part of this number is 3 and the imaginary part is 4. To plot this, we draw a point 3 units to the right of the origin in the horizontal direction and 4 units down in the vertical direction. Because this is an analogous to the Cartesian coordinate system for plotting points, we could think about plotting our complex number z equals a plus bi as if we are plotting the point AB in the Cartesian coordinates. Sometimes people write complex numbers as z equals x plus yi to highlight this relation. Arithmetic on complex numbers. Before we dive into the more complicated uses of complex numbers, let's make sure we remember the basic arithmetic involved. To add or subtract complex numbers, we simply add the like terms, combining the real parts and combining the imaginary parts. Example 3. Add 3 minus 4i and 2 plus 5i. Adding 3 minus 4i plus 2 plus 5i, we add the real parts and the imaginary parts. 3 plus 2 minus 4i plus 5i, 5 plus I. We can also multiply and divide complex numbers. Example 4. 4 multiplied by 2 plus 5i. To multiply the complex number by a real number, we simply distribute as we would when multiplying polynomials. 4 multiplied by 2 plus 5i, distribute, equals 4 multiplied by 2 plus 4 multiplied by 5i, simplify, equals 8 plus 20i. Example 5. Multiply 2 minus 3i multiplied by 1 plus 4i. To multiply two complex numbers, we expand the product as we would with polynomials. The process commonly called FOIL, first, outer, inner, last. 2 minus 3i multiplied by 1 plus 4i, expand, simplify, equals 14 plus 5i. Example 6. Divide 2 plus 5i divided by 4 minus I. To divide two complex numbers, we have to devise a way to write this as a complex number with a real part and an imaginary part. We start this process by eliminating the complex number in the denominator. To do this, we multiply the numerator and the denominator by a special complex number so that the result in the denominator is a real number. The number we need to multiply by is called the complex conjugate, in which the sign of the imaginary part is changed. Here, 4 plus I is the complex conjugate of 4 minus I. Of course, obeying our algebraic rules, we must multiply by 4 plus I on both the top and bottom. In the numerator, 2 plus 5I multiplied by 4 plus I equals 3 plus 22I. Multiplying the denominator, 4 minus I multiplied by 4 plus I equals 17. Combining this, we get 3 plus 22I divided by 17 equals 3/17 plus 22I over 17. With the interpretation of complex numbers as points in a plane, which can be related to the Cartesian coordinate system, you might be starting to guess our next step. To refer to this point not by its horizontal and vertical components, but using its polar location, given by the distance from the origin and an angle. Polar form of complex numbers. Remember, because the complex plane is analogous to the Cartesian plane that we can think of a complex number, z equals x plus yi as analogous to the Cartesian point, xy, and recall how we converted from xy to polar r theta coordinates in the last section. Bringing in all of our old rules, we remember the following. With this in mind, we can write z equals x plus yi equals r cosine of theta equals I r sine of theta. Polar form of a complex number in Euler's formula. The polar form of a complex number is z equals r cosine of theta plus I r sine of theta. An alternate form, which will be primary when used, is z equals re raised to the I theta power. Euler's formula states re raised to the I theta power equals r cosine of theta plus I r sine of theta. Similar to plotting a point in a polar coordinate system, we need r and theta to find the polar form of a complex number. Example 12. Evaluate -4 plus 4i raised to the 6th power. While we can multiply this number by itself 5 times, that would be very tedious. To compute this more efficiently, we can use the polar form of the complex number. In an earlier example, we found that -4 plus 4i equals 4 multiplied by the square root of 2e raised to the 3/4 I power. Using this, -4 plus 4i raised to the 6th power equals 32,768 e raised to the 9/2 I power. At this point, we have found the power as a complex number in polar form. If we want the answer in standard form, a plus bi form, we can utilize Euler's formula. Since 9/2 is coterminal with pi-halves, we can use our special angle knowledge to evaluate the sine and cosine. We have found that -4 plus 4i raised to the 6th power is 32,768i. The result of this process can be summarized by de Muevas Theorem. This is a shorthand to using exponent rules. De Muevas Theorem, if z equals r multiplied by cosine of theta plus I sine of theta, then for any integer n, z raised to the n power equals r raised to the nth power multiplied by cosine of n theta plus I sine of n theta.